In this video we're going to look at how we can approximate our first three hyperbolic functions using the CORDIC algorithm in vectoring mode. So in vectoring mode we're going to approximate the inverse functions, that is inverse cosh, inverse singe and inverse tange. So this example here we generate the inverse tange function. So we start off with our CORDIC algorithm. Now note, first of all, that the CORDIC algorithm's subscript is now a value of j as opposed to a value of I. And we can relate these via j is equal to I plus 1. Now we'll see just in a moment why we have to do this. The initialization is x0, y0 and z0 are x in, y in and z in. And these will become more apparent whenever we look at it in the graphical calculator. And it's going to give us an output xn, which is an the root of x0 squared minus y0 squared, and yn will finish up at a value of 0, and zn will be z0 plus the inverse tange of y0 upon x0. And again we have the value for our an. Now the one we're really interested in here is this Zn, because it's going to give us our inverse tange function. So let's start off by working out why we have changed the subscript to j, and we've got this j is equal to I plus 1. Now whenever we want to work out our final angle Zn, we're going to add on this arctange y0 upon x0. So let's have a look at the tange function first of all, and we'll see from that where we get this j is equal to I plus 1. So this is our tange function here. We're going to go from angle to length. Now whenever we work out our value for our Zn, we're going to have to use the arctange y0 upon x0, so we're going to go from the length here back to an angle. And we've said previously that we do this in fixed amounts. So we start off with a value of 2 to the minus 0, which is a value of 1, and then we go to 2 to the minus 1, which is 0.5, and then 2 to the minus 2, which is 0.25, and then it goes down to 0.125, and it keeps halving, and so on and so forth for our 9 iterations. And then we read our angles off from the graph here. So if we were to say start at a value of 1 here, for instance, for our value for our j, then we're going to have 2 to the power of minus 1, which is 1 upon 2, which is a half. And a half here is going to come along and it's going to give you this angle here in radians, 0.549. And then we would go on to the next one, which would be a quarter, which again would give you this angle here. And you can see the angle is actually written up here as well, which would be the value 0.25, which in radians 0.255, and in degrees is 14.63 degrees. The next one we give you a value of 7.199, and so on and so forth. Now we've seen this previously when we looked at the other simulations that we've done, but the difference here now is that the function here, tange, isn't defined whenever we have the value of 1. So if I go to the value of 1 here, you'll see that at this point here we would just be tending off towards infinity. So we can't use the first value. So the first value previously we were using would have been a value of 45 degrees, but we can't use that. So we're going to have to, instead of starting off at a value I is equal to 0, we're going to have to start off with a value I is equal to 1. So we give that I is equal to 1, we just give it a new name and we call it j, and we say j is equal to I plus 1. So we're actually starting from this point here, and our first angle is 31.472924 degrees, and then our next angle is 14.634076. So we're just having to start off at the next value up because the inverse Tange function is undefined at a value of 1. Now this table here shows a list of angles that we're going to use for our hyperbolic rotations. Now don't worry too much about this for the moment. It'll become more clear whenever we look at it in the actual simulation, which we'll have a look at in just a moment. But what we've got here really are two sets of angles. We've got our arc Tange 1/2 to the j, which is this set of angles here. And we've also got a copy of these in this column here in radians. And we also have our set of angles which is given by 1/2 to the j, which are these angles here. And these are the same as we've seen in the previous video when we looked at the linear and also when we looked at the circular approximations. And we've also got those angles in radians. And you'll notice here that the first iteration here, it's undefined because our value for our arc Tange of a value of 1 is going to be undefined. So what we're going to do is we're going to add on an extra iteration here. Because we've lost one of the iterations here, we'll just add an extra one on at the bottom. So now it's going to run from 0 to 9 as opposed to 0 to 8. Now there is one other complication which I'll talk about in a different video, but we'll just mention it here, and that is that in order for the hyperbolic version to converge, that is, it's going to give the correct value for our gain, then we're going to have to repeat step 4 twice. So you see here I've actually got the step 1, 2, 3 and 4, and you see the line for step 4 is exactly the same for the line for step 5, so we've had to repeat it. Now again, I'll go into detail as to why that is in a different video, but we can just accept that for the moment as part of the algorithm. So let's go ahead and we'll see how this works in the simulator. So let's take our time and work through the example. We have our unit circle here and we have our hyperbola. Now we're going to start off with a point on the unit circle. So just to keep it the same as what we have worked out previously, we're going to use the point 0.866 and the y point will be 0.5. So what we're going to work out then is the inverse Tange of the division between these 2 points. So what's going to be end up working out the inverse Tange of 0.5 divided by 0.866. So I've added in the CORDIC algorithm, the initialization and also the output into the graphical calculator here. Now let's say we start off with 2 familiar lengths which we've used previously, and that's going to be 0.866 for the x and 0.5 for the y. So with those distances here, 0.866 for x and 0.5 for the y, it's going to map out a circular angle of 30 degrees. Now remember, what we're looking at here now are hyperbolic angles. So if I was to put in the value for our hyperbolic angle, this would be this angle here. Now remember, the circular angle can be given by the area of the triangle. So if we look at twice the area of this triangle here, then it's going to give us the circular angle in radians. Now equivalently, if you look at this brown line here, then the hyperbolic angle is going to be given by twice the area that's generated within this area here. And we've seen that previously whenever we moved the circular angle. You can see the circular angle generated with the blue vector here and the hyperbolic angle generated by the brown vector. And you can see that what maps its way around when we get round to the 180 degrees, it tends off towards the asymptote y is equal to x. And again, whenever we work it round in the minus 180 degrees, it works round and it generates the negative values. So we've seen that in a previous video when we looked at the basics of the hyperbolic functions. So let's start off with the value for our z0 being z in, which in this case here is going to be our 30 degrees. And we've got our value for our y0 and x0. So our y0 and our x0 are just the values of our 0.866 and our 0.5. So that's the initialization setup. So what we do is we rotate this point in order to ensure that the value for our y tends towards 0. So we're going to first of all rotate this by our angle. Now the angle we're going to rotate it by is going to be the 26.565 degrees. So remember, we don't rotate it by 45 because the inverse tange of our value for 1 tends off to infinity, so it's not going to work for us. So we're going to start off with the next value along, which is a 26.565. So now, having rotated this around in by that value, we're then going to have to add the angle on. So the angle we're going to be adding on is the arctange 2 to the minus j. So that angle from the table which I have just shown you is going to be an angle of 31.47 degrees. And I have all of the angles already generated here from the simulation. So we're going to be taking our original angle of 30 degrees and we'll add on 31.472924. So I'll add that on just now. Plus 31.472924. So try not to get lost in the details here. We have the same sort of setup we had when we looked at the linear mode. We're going to have two sets of angles. We're going to have one set of angles that we use in order to rotate this blue vector here. And it's going to be given by the arctange 2 to the minus j. But we're also going to have another set of angles which we use in order to ensure that the value for our yi will tend towards 0. And those are going to be given by the 2 to the minus j. So we use this set of angles here to bring the y value down to 0. And we use this set of angles here to add and subtract values onto the original angle of 30 degrees. So we check our height here, and you can see that our height here is still a positive value. So we rotate this again in the clockwise direction by the next value, which is 14.03 degrees. So it gets rotated in this direction. Now, whenever we've rotated this one, we're going to have to change this angle here as well. So we're going to go and we're going to add on the value for that angle. And the value for that angle is going to be 14.634076. So I'll add that on just now. So we add on the 14.63076. And that gives us our next approximation. And you can see that the value yi is now negative, so we're going to have to rotate this in the anti-clockwise direction. And we continue again here, so we rotate it in the anti-clockwise direction. And having done that, we're going to have to change this angle once more. So what I'll do is I'll work through all of the iterations now until we get to the final result, and we'll go and have a look at the final result. So I've worked through all of the iterations, and you can see that the final value down here is given by this little pink dot, and you can see that it's a value of minus 0.00146. So the y value here is in effect tending towards 0. So if the y value has tended towards 0, then it means that the final output here for our Zn is going to be the original angle Z0, which is our 30 degrees, and the plus the arctange y0 upon x0. So let's go ahead and we'll check the values out and see if this has actually occurred. So as we have rotated this point here in order to get the y value towards 0, with each of the iterations we've added on or subtracted off the values of our angles, which are given by our arctange 2 to the minus j, and that has given us a final angle here of 67.886769 degrees. So let's see whether this is the angle that we expect to get. So here are our final results. We have our algorithm which tells us Zn is equal to Z0 plus the inverse tangent of y0 upon x0. So we start off with a value Z0 and we'll put them in degrees, so that's 30 degrees. And we're going to have the arctange, the y0 upon x0, well y0 was 0.5 and x0 is 0.866. But we're going to have to convert this from radians into degrees, so we do that by multiplying by our 180 and dividing by our pi. So this part of it here, if you put this into a calculator, it's going to give you 37.7285 degrees. So when we add both of these together, we should get an angle of 67.7285 degrees. So this is the angle which we are planning on generating from our algorithm. Now if you follow through the algorithm, we're going to get the value for Zn as our initial angle of 30 degrees, and we're going to be adding and subtracting the multiples of these angles here. So I won't read through them, but these are the angles that you've seen in the spreadsheet. So whenever we add all of these up, we're going to get 67.7878 degrees. So you can see here that this angle here, 67.7878, is our approximation, and the actual angle that you get whenever you work out the arctange is going to be 67.7285. So we can see here that if we were to take off the initial angle of our 30 degrees, we're going to have the arctange of 0.5 upon 0.866, which will give us 37.7 degrees. And our approximation is going to be 67.7 minus the 30, which will also give us 37.7 degrees. So we can see here that we are actually correct to within 0.1 of a degree. So we have worked out the output here, Zn, and we've also seen that the value for our yn will tend towards 0. Now the value for our xn is going to be given by this term here. So it's going to be the 0.866 squared minus 0.5 squared, and we take the square root and we multiply it by this gain factor an. And again, our gain factor an is given by the product of the root of 1 minus 2 to the minus 2j. So let's quickly go ahead and we'll figure out what this value for an is. So the value for our an is given by the product of our root of 1 minus 2 to the minus 2j. Remember, j is equal to I plus 1, so I starts at 0, so it means that j must start at a value of 1. So j will run through the values 1, 2, 3, 4, 5, 6, 7, 8 and 9. So in order to work that out, we're going to have the product of 1 minus 1 upon 2 to the 2, 1 minus 1 upon 2 to the 4, and so on and so forth. Now the one thing to notice here is that the fourth term gets repeated. So this is the fourth term being repeated in it, and remember we needed to do that in order to ensure that we had the right value for the gain, and also that the value for our inverse tangent x would converge. So this, when we work it out, is approximately equal to 0.828 16147. So this is just like the gain factor we worked out previously whenever we looked at the circular algorithms. So this here is our gain factor. Now the value of our xn is going to be given by the gain factor times the root of our x naught squared plus y naught squared, and that gives us a value of 0.585575. So let's have a look in the graph in the graphical calculator and see whether we get this value. So you can see from the graphical calculator the final value that we got is 0.5858 for our x value. So if we round up this, you can see that we're going to get the exact value that we generated in the graphical calculator to 4 decimal places. So there was quite a lot involved in this video. Take your time and possibly work through a couple of the iterations of the algorithm using a pen and paper, and also open up the graphical calculator simulation in the resources section and have a go with it yourself. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.